Well, thank you, Tim.
Over to
Thank you. First off, yeah, thank you to Integer for inviting me to be back to talk with you today. I'm going to switch gears a little bit today compared to some of my previous talks. Usually I'm really energetic and lively and jumping around, and, Sean kind of fired me up with some of his discussion a minute ago, so I'm going to talk technical today, show you some details of the low NOx work that we're doing at Southwest Research, especially the work that's being done as part of the ARB low NOx initiative, the demonstration program that was discussed earlier by Bill Robertson. Before I start, though, going back to Sean Waters' comments in regard to billions of gallons of fuel saved and lost and those kind of things, and I was thinking about it, and this is a DEF conference in many ways, and it's about lean burn technology and after treatment. Let's go back 30 years and talk about the bad guys, those light-duty gasoline stoichiometric folks that developed a catalyst that didn't run lean, didn't use lean burn. And so, in some ways, you got to look back and think about a future. And so something like 10% fuel energy was given away to being stoic instead of lean for all these years. And if you think about 140 billions of gallons of gasoline a year used in the United States only, that's how many gallons were turned into CO2 over that period. So maybe, as we watch the truck industry kind of plateau in total sales in the future, we'll get back there again. And we've got SCR on every truck and filters on every truck. Maybe we start looking back at the gasoline business and saying it should be a lean burn business. And now that I'm going to show you today some 99.9 SCR efficiencies that are being achieved warm. And so we're getting pretty close to that three-way catalyst kind of efficiency now. So maybe it's time we think that way again. Okay, enough of an introduction. Let me make sure that I know how my slide advances. Green button, Tim? Yes. Okay, so this is a copy of what's in your agenda packet. I'm going to talk about ARB, and then we want to talk a little bit beyond that, how to ensure technology success that's outside or beyond the regulatory discussions, and then what is the feasibility of a broader federal NOx standard. And I can only really repeat a little bit of what was said this morning by Matt Spears and Bill Robertson, but I'll give my spin on it a little bit when we get to it. This is going to be like a language lesson, folks. Get ready. There's a lot of acronyms built into the technologies, but, don't sweat it too much. I'm borrowing from the slides that we prepare and deliver to ARB as part of our work at Southwest Research as the data provider for this demonstration program. And so all of this is on the ARB website, and I'll give you a link at the end if you want to follow up a little bit more. The objectives of the ARB program are to demonstrate a 90% NOx reduction versus the current heavy-duty 0.2 gram per horsepower hour NOx standard. We've talked about it this morning quite a bit, but 90% is pretty significant. It's another 90 on top of that last 90, as a previous speaker said. And we want to do that with aged catalyst parts, and so we want to show that through the life of the vehicle that we'd be able to maintain this kind of emissions goal. The solution that we find needs to be technically feasible, but maybe beyond technical, it needs to be consistent with the path that also supports a greenhouse gas standard of the future and improved fuel economy. So it's ultra low NOx, but it's ultra low NOx with ultra low CO2 ultimately. There's two engines in this program. Diesel engine on the left, 2014 Volvo, a Euro 6 calibrated engine. You can see the specs on it. This is a cooled EGR DPF SCR solution as the basis. I think the key feature I'll show you on the next slide is that it's a turbo compounded engine, and so this engine has a mechanical turbo compounder downstream of the turbocharger that's it's there to create as a waste heat recovery device. So improving fuel efficiency towards the future, improving CO2 numbers. However, that turbo compounder is a fairly large piece of equipment that's between the engine and the catalyst system, and so it has to get warm before any of the catalysts do in a cold start. And so it's really a detriment to achieving low NOx fast. And so in many ways, this engine, it represents a future low CO2 option, but it also represents a difficult future option to make low NOx with. So if we can do it with this one, it might be that we can do it with several of the other technologies that are being mentioned by many people in the world. On the right side, the CNG engine is a 2012 Cummins ISX-12G. That engine is outfitted as a three-way catalyst engine in our work. We've applied a different controller with some different controls logic, but it's basically a close-coupled three-way cat with an underfloor three-way cat using switching algorithms very similar to gasoline-type technology. And to cut to the chase, that engine makes 0.02 without too much difficulty. And I can show you some more numbers in the end if we have time for it. I'm going to spend most of my time today talking about the diesel engine because it did require a larger effort to test all of the catalyst arrangements that we worked with and the different after-treatment options. Close-up of the turbo compound engine here shows you a little bit of the detail that we're talking about. You can see the primary turbine right in the middle of the plot, and then the secondary or the downstream turbo compound turbine and the exit of the exhaust. On your plot, it's on the upper left, the exit. But all of that extra material in the exhaust path, you have to heat that up before you get the catalyst hot. And so it's definitely a technical challenge to make that work, but it's one that we knew we had when we walked into this project. Also, you can kind of see the operation of a turbo compounder. Downstream of that turbo compounder on the left, you can see a gear arrangement that goes down to the lower left, and so you attach that second turbine to the crankshaft of the engine through a mechanical and hydraulic coupling. Of course, turbo compound is only one type of waste heat recovery system that is being looked at for the future. So we've got mechanical turbo compound, electric turbo compound, variable types of supercharger turbo compounders. You could even go to then the Rankine cycle systems, as our Cummins speaker talked about, and then even beyond that. And so I'm hoping that I'll remember at the end of this talk to say a few words about even some crazy stuff like supercritical CO2 waste heat recovery for heavy trucks. And Southwest Research has recently dived into some of that, so I'm going to try to say a few words. So the ARB program is primarily focused on the heavy-duty FTP test. However, we're including the WHTC, the RMC SET test, which is more of a steady-state type of test, the carb idle. Down at the bottom, we bring in some vocational cycles as well, and these are the low-load, low-temperature cycles that everybody's discussing today. So it's really the off-cycle kind of stuff that we've been mentioning. Basically, the bottom half of this graph talks about the end of our project and the start of the next project. One of the speakers this morning, Dr. Robertson, mentioned that there's a second program that ARB has funded that's a follow-on to what I'm talking about today. So the first half is what we've done to date, and the second part is coming in the follow-on program where we're going to look a lot at the lightly loaded and low-temperature cycles. And the results of this will be quite interesting. I'll show you a couple of those at the end of the slides. So our starting point for the diesel and the CNG engines are shown left to right here. Basically, this graph is out on the ARB website as well, but it says that we started out with a diesel engine that's about a 3 gram per horsepower hour NOx engine. That's engine out. And so that gives you an idea what the tuning of the engine is today. About a 3 gram engine, and that engine across the composite cycle today makes about a 0.14 grams per horsepower hour NOx tailpipe number. So it's a well-tuned engine, and it does quite nicely to be below today's 0.2 standard, but now we've got to go that 90% total for our goal. And the CNG engine as well was a 0.115 gram per horsepower hour engine, and now, as I mentioned, it's well below the 0.02 standard. The strategy for this program had to be limited. In all, we considered over 500 different after-treatment options to start the program. You can't find a budget to do that much work, so we came down to 33 options that would be tested in one way or other during the project, and then ultimately down to 4, and then to 1 final demonstrator for the diesel engine. Here, to limit our efforts for total calibration, we spent most of our time working on the cold start portion of the cycle to see if we could get enough NOx reduction during cold start to allow us to have some balancing and budget to use during the hot operation as well. It turns out in the end, we actually did improve some of the hot operation NOx through small changes in strategy, but a larger piece was taken in the first 600 seconds during the cold start. And you can see the red new calibration versus baseline where our temperature at the turbocharger outlet was increased substantially during cold start through things like simple use of timing, retarded timing of the engine, changes in EGR calibration, things like that. Again, this program was primarily focusing on after-treatment systems and how we could use those for this program. The engine side work could be extended quite a bit further, and so there's a balancing ultimately of the technologies that would be chosen for the engine side versus after-treatment that could achieve some of the same results. This slide was shown earlier, so I'll go over it pretty quickly, but basically it's guiding your eyes to different solutions to try to meet the low NOx target. Left side of the plot generally shows more traditional approaches with urea delivery as DEF to the SCR catalyst. Yeah, we can get something on the order of a 50 or 60% reduction in NOx through application of technologies in that way. In the middle of the plot, we show that heated dosing or delivery of ammonia as a gas as a primary label here allows us to have several options that might be able to approach the 0.02 NOx standard or the 0.02 NOx target. And then finally, on the far right, I'd call it more of the sledgehammer. If you put a diesel burner in the exhaust of the truck, you can deliver fuel, you use an igniter, and you control a flame right near the catalyst, and you can put the fuel energy directly in the place where you want to put it from a catalyst standpoint. And so yes, you can heat up catalysts substantially if you've got a burner in the exhaust, and so the burner-based systems show up pretty clearly as potentials for getting to the O2 target. The targets that I'm showing you, the data I'm showing you here was not generated from engine work. This was generated from a what we call a hot gas transient reactor. So it's a burner system that mimics a diesel engine very closely. So we run our baseline diesel engine to get a cold start profile, engine out. Then we replay that profile with a burner where it reproduces the mass flow rates, the temperatures, the NO, the NO2, the hydrocarbons, almost reproduces PM. That's not something that's perfected yet. But from a NOx standpoint, it's a great way of very quickly assessing the potential of many different aftertreatment systems. You don't have a dyno, you don't have an engine, you don't have to wait for the whole thing to cool down so you can do another cold start. You just swap parts in and out and redo the start over and over again. So it allowed us to look at a large number of options. Out of those 33 options that were considered, this graph has got way too much on it, but there's a red box around the top that shows you 1, 2, 3, 4, 5, 6, 7 different combinations of after-treatment technologies that we looked at. Today I'm going to talk about 3 or 4 of those, but this table is on the ARB website and it sets up the prioritization for the testing sequences that we did. So it's top to bottom, those are the options. So configuration 1 from that table is a partial NOx adsorber, where we adsorb NOx at low temperature. When this catalyst reaches a certain critical temperature, the NOx is released and has to be handled somewhere else. But it's kind of a sponge for NOx during the cold start. You can see downstream from that, we've got a DEF injector injecting urea across an electrically heated catalyst. That electrically heated catalyst then provides ammonia to the SCR that's on filter, with a downstream SCR and then a cleanup catalyst. And so this configuration was tested in the screening process with the burner rig, and then it did go to the engine ultimately, to the diesel engine. The results are shown here. So we achieved about a 0.025 to a 0.03 gram per horsepower hour with this arrangement. That used a 2 kilowatt electrically heated catalyst in the EHC area of the diagram. We also tested with a 6 kilowatt electrically heated catalyst. We're able to reduce the NOx numbers to about an 0.22 up to an 0.25 or so. So not fully meeting the target, but we're getting pretty close already with this arrangement. So I would say that if we did not have a turbo compounded engine, we'd probably be within the target range for 0.2 grams with this setup. So configuration 1, I've got a graph here showing temperatures in NOx. Really, I'll just guide you to the highest curve on the graph, the bright red. That represents the SCRF inlet temperature. And so you can see that if we read across to the right-hand side, I'm looking for the 200 degrees C line. We generally achieve 200 degrees C at about 250 seconds. Just for reference, most of today's heavy-duty diesel trucks, you get to about 200 C somewhere in the 500 to 600 second range, usually closer to 600 seconds, just the cycle is based that way. Moving on, if I put 6 kilowatts of heat into this, and I'll try to back up, so watch that top curve again. So now I'm going to go from a 2 kilowatt electric heater to a 6 kilowatt electric heater, and you can see that 200 degrees C occurs somewhere around 250 seconds again. So we need more electrical heat than this if we want to really advance. And that's because the test cycle has a couple of distinct high load portions that are separated by significant idle portions in the first 200 to 300 seconds. Moving on to configuration 2 in the diagram that I showed previously, the table. Now we go to what we call a light-off SCR. So it's a close-coupled SCR catalyst that has an ammonia delivery coming from an electrically heated ammonia generation system. That ammonia is put into the light-off SCR for fast light-off. It also has a downstream introduction point beyond the PNA, going into the more traditional SCR, but SCR on filter. So kind of a similar arrangement to the last one with some changes for the light-off SCR. This package also produced about an 0.22 number for NOx, so it's very similar in overall NOx, but the greenhouse gas penalty, the fuel penalty, was slightly less. The previous option I showed you was somewhere around 2% fuel energy given to the process that we're testing. This one somewhere on the order of 1%. But 1%, but we're not at the standard or at the target. I apologize, I'm using the word standard. So we're not at the target yet, and if that target was a standard, then we would make a new target that's somewhere down in the 0.015 range or even lower, so that we'd have some engineering margin to use in the future. So again, now I'll show you the close-coupled light-off SCR catalyst is the black curve in the top figure. The red curve is the 6 kilowatt electrically heated catalyst curve from the previous pages. You can see that the close-coupled light-off catalyst, it gets hot very fast. We got to 200 degrees C by about 60 seconds for that front catalyst. So we can start doing some NOx conversion pretty fast with this option. But the lower slide indicates a reversal of trends. You put in some mass up front, and it's working to reduce NOx to some extent, but the downstream SCR is not getting hot as fast as the other one did, so we've traded off a couple options for each other here. Moving to another option that we considered in that table. This one was configuration 3 from the previous slides. Configuration 3 had an electrically heated catalyst followed by DOC, and then a DEF injector followed by SCRF, SCR, and ASC. This combination, when we started to look at it in the screening process, it turned out that it would require too much energy to create the temperatures that we needed to get the conversions that we were after. So this was not brought to the engine ultimately. We created an alternate configuration 3 that looks a little bit more like the first configuration with some small changes. Here we've got a different partial NOx adsorber. It's got a different catalyst. So we call it PNA2. It's followed by a DEF doser across an electrically heated catalyst again, followed by, now we've got SCR, SCRF, SCR, and then ASC. So you guys can imagine that I can draw these cartoons as small as I want. So I can make this after-treatment system look pretty small, but I'll tell you straight up that the volumes are getting pretty large, and it's technically feasible, but as someone who's working on the research work and on what would we do over the next 10 years or so, getting ready for all of this, we would be working hard to bring volumes down and to bring precious metal out and to make packaging easier. So it's the same exercise we always have. So, you know, the lab guys, I admit it, lab guys get to go in the lab and make the data work, and we're showing feasibility, but there is engineering and there's production side stuff that has to be thought of ultimately. Again, you see numbers like 022 to 025. It looks like getting down below 05 is doable. Below 02 was elusive in some of this work. Finally, we get to configuration 4. This is the sledgehammer that I talked about. So the mini burner was introduced in that table as option 4. It became really our 6th option that I've showed you today. Now, the budget of this program said demonstrate. And so when we got to a demonstration that hit 02, the budget had been expended a long time ago. So I wanted to let you guys know that there's not 33 more that we have full data sets for. Instead, this is the last I'll show you today, but what we've got, a partial NOx absorber followed by a mini burner. And once again, a mini burner is a small combustion device that can produce 10 kilowatts up to 30, 40, 50, depending upon how you size it and all of that. But it's a small engine without a piston. Doesn't do any work, it just heats up catalyst. So you've got to have some kind of igniter, a fuel source, an air source, and then all of the materials and engineering. Of course, these burners have been put into production before in non-road applications even today, and so they could be brought to this application for cold start. So you can see the configuration. Here, we've got a composite of about 0.012, so we're well below the O2 standard with this configuration. We've got about a 2% fuel penalty on the FTP, about a 0.5% due to engine calibrations, a 0.5% for SCRF, and about 1% due to the mini burner consumption. And so we've tried to put it together that way to give you a little bit of explanation. Now, this is not our final demonstration. These numbers may change. So I'll show you a couple of temperature plots again before we go on to the next step in the program. You can see again the bright red, we're finding 200 degrees C in less than 100 seconds. And really this is about how fast do you light the burner and how much energy do you want to put on the catalyst. And so there's some balance and some calibration that can still be accomplished. You can see, I want to guide you now to, for example, let's look at SCRF, hang on, I'm looking for NOx. There it is, purple, SCRF outlet NOx, and it's down at the very bottom of the plot. Around 50 seconds, you'll see a little bit of breakthrough, and then at about 250 seconds, a little bit more. Now, our hope is that 250 and anything beyond it becomes a 0 pretty fast. That gives you a low NOx number. You can see the scales changed here, so we're talking about not even the 600 seconds of the cold start that most of us worry about with heavy duty. After this, it's all 0. It's really this first few hundred seconds now, very much like a light duty vehicle, where you're controlling so much NOx that any breakthrough is really important and gets concentrated on. I'm going to jump by that one. So jump into the table that says this is our preliminary engine-based FTP test with that configuration 4, the mini burner. Our average is about a 0.011 composite for cold and hot. The cold test is running about a 0.025 average, and the hots are triple, double zeros with a digit on the end. So it is starting to look like light duty type of NOx data. Engine out NOx, our current calibration is about 2.9 grams, so similar to the 3 grams that we had when we started with this. Cold start conversion is about 99%, and the hot start's about 99.7 now. N2O, we talked about it this morning, said there's a 0.1 gram kind of limit. We're at 0.7 to 0.8 grams for these calibrations. Okay, looks pretty good, but somebody should yell at me because how did you age those catalysts and what are you testing? While we're setting up the first demonstrations and the screening, we're using oven-aged parts. we're going to be using fully aged parts or nearly fully aged parts in our final demonstration. And that's going to occur, I suspect it'll happen this month or early next month. The aging process is occurring right now, and we should be finished. We're using an aging protocol that was created at Southwest Research on an earlier consortium program that uses both thermal and chemical accelerated aging. We're going to run 1,000 total hours, and I think we're at about 800 plus now. So as soon as that's done, all of these catalysts go back on the engine, and we do the final demo to see if those sub-O2 numbers are still available to us. I mentioned the follow-on program that's from ARB. It's already been awarded. It's just a little bit over $1 million funding. The focus of that program is going to be low temperature and low load. So everything we've done so far, we've tuned the engine, we've put on a pretty amazing after-treatment system from a number standpoint, that's definite. What are we going to do to that to make it work at those off-cycle conditions? Here's a little bit of early effort that I can show you. I apologize, there's a lot on the screen, but on the upper left, what you're looking at the top is engine speed, and you can see that there's a long idle segment for about 30 seconds or so. So we're idling at 600 RPM for that entire period. Then we get a bunch of speed changes, and what those represent is the New York bus cycle. And so the New York bus cycle is the highly transient piece to the right. So to start this test that I'm showing you, we ran that bus cycle 4 times back to back. No idle, just 4 times back to back bus cycle. That set up the initial conditions for the drop to idle. We idle for 30 seconds and then go back into the New York bus cycle, and you can see all the temperatures of the after-treatment systems dropping off during that idle. And you can see that this New York bus cycle, there's a lot of speed changes, but not much load change. You're not carrying that much weight with a city bus. And so the average power of the cycle is only 17 kilowatts. So you're taking 17 kilowatts out of hundreds plus kilowatts. And so engine out, you've got a 6-gram NOx engine for this operating mode. Tailpipe with catalyst, about 2.4 grams per horsepower hour. So that gives you about a 62% conversion from a system that should be able to give you an O2 on the FTP. So there's definitely attention that has to be brought to the light load, light duty piece, and you can see it real clearly here. Now this cycle is very lightly loaded, and it doesn't do much to keep the catalyst hot. So there's going to have to be more thermal maintenance that's brought. If it's a burner system, maybe the burner's got to be run during the cycle more, and so that's the next phase of our program. The bottom right shows NOx numbers that would go with the temperature numbers I showed you. I won't stay on that slide. Chances for a new federal NOx standard? Well, I just copied the stuff that the guys put up this morning for you. The petitions, somebody said 2,000 pages, and I think somebody said 4,000 or 5,000 pages, but there's a whole lot of petitions and then responses to those out there. I can't say anything official because I'm not an official. I'm a lab operator. I run a big emissions lab with a lot of dynos and Horiba benches. But I do see what you guys see when you try to read that 1,690 pages plus. And it seems to say that in a greenhouse gas regulation, we see pretty clearly that there's plenty of discussion of NOx. And so no doubt ARB is having to do something because of ozone standards. That ozone standard is federal, and it's now 70 ppb across the United States, and so that's going to push us to decrease ozone again through some kind of NOx regulations across many industries. So I'm preparing for it, and that's really the best I can tell you. Now, in whether it's real or not, let me jump past the thank you to everybody who funded the program and worked with us. I'll jump ahead a little bit and say that, outside of these kind of programs, Southwest Research is also working in several areas where we're working with private companies and beyond. The Cooperative Research Act of 1984, I believe it is, allows us to do work like is being done in this conference, where we can work without breaking antitrust laws if we look far enough into the future and we work on technology research that's important to groups of companies. And once that research is established some data baselines, then each company can go and develop that towards a production situation. So our Clean Diesel Consortium and our ACAT consortiums are good descriptions of how we can take these regulatory goals that we're just starting to see, and then we can think 10 or 15 years in advance on, can we do it in a different way? Something that's not what we just showed you in the last 25 slides. And so the Clean Diesel program is 25 years old. We've got about 25 companies. All the OEs in the room here, I think, are members of it. ACAT is a catalyst research program. So one of them concentrates on engines primarily, the other catalysts, but no doubt there's some talk between the two. On the right, I'm showing you a slide that you've seen a little bit of, but it really brings out some of what's going on, combustion system and engine-wise. On the upper left, there's the cross-section of a piston bowl and the combustion chamber, half of a diesel combustion chamber, and then the fuel injection and flame that's being issued. Back in pre-2010, we were working on very high EGR solutions, trying to determine whether SCR was going to be necessary. So a bowl that looks like the one on the upper left is very effective at reducing particulates, creating a good mixing process for a high EGR engine, but you can see that the fuel consumption is somewhere in the 205 grams range. It was fairly high. As we move down that orange curve and into the green curve, you can see off to the far right, that's Clean Diesel 6 from 2 years ago, up to 4 or 5 years ago now. A different shape combustion system fully. That combustion system gives very high NOx. You can see the bottom axis, 25 grams NOx. It's pretty far from 0.02. But the fuel consumption's wonderful. That's a 49.5 or so brake thermally efficient engine. So one of the highest in the world. So how do you join those two curves together is the real key. And the yellow points that I'm showing moving from right to left, that's the low pressure loop EGR option that was discussed earlier today. You bring low pressure loop to that kind of high NOx engine, the pumping losses are not too bad, and you can climb over to the left where we're trying to go to. And so combustion system, turbocharging system, and beyond. So finally, I'll end by saying waste heat recovery one more time. Southwest Research runs these programs as a typical exercise for looking at future technology. But some future technologies are bigger than these programs can handle. And so one of them that comes up is waste heat recovery. It's a big topic, it's an expensive topic. Southwest Research was lucky enough over the last 2 months to win a DOE grant of $80 million to look at supercritical CO2 as a waste heat recovery system for power plants. So we're going to build a 10 megawatt system on campus. But what that means is that we're going to have all the tools and all the experts and all the right people in the right place to do more in this area of supercritical CO2 waste heat. It's a tough one. It's high pressure, it takes heavy heat exchangers, and it's got so much energy in the fluid that the turbine to produce 1 megawatt of power is about the size of a nickel. So if I only want 35 kilowatts to 50 kilowatts, I have to have a different kind of expander. But that's the kind of stuff that I think that some of us have to do. If I can leverage that $80 million and get a little bit of work going on here, we'll look at things that are outside of the scope of the other research projects so we can see if there's something that's crazy on the horizon. Okay, I'll end it there, and I don't know if we have time for questions. In the slide package, I included CNG engine results as well. It's hitting the O2 number quite readily, and so those numbers will be released as well with the end of the ARB program. Thank you.
Thank you, Charles. We do have time for 1 or 2 questions before we break, so please raise your hand if you have any. I'll start, Charles. Can you just, in terms of the low NOx program, what's the current status? How close are you to finishing? What's left to do?
The final demonstrations will be next month.
Yeah.
And final reports. And
So
that's
nearly there.
pretty much it.
Yeah.
Yeah, we're very near the end. I left out the schedule slide, but we're very close to ending the program now.
And the configuration you showed us, that's going to be the one that you're going to demonstrate?
That will be the demonstrator that we will use to be our primary demonstration. Yeah.
Thank you.
Again, I would point out, though, that many of the other options that I showed were very close to O2, and depending upon the after-treatment and the waste heat recovery system that's chosen, several of those might be able to fit into that box.
So do we have a question, Ali? Any questions before we break? Yes, on the left. So we have two. Yep. Thank you.
Hi, you mentioned the calibration changes that you did had quite a bit of benefit. Could you say more about what those were or go into more details?
Yeah, basically, it's the kind of stuff that first level calibration change. So the cold start work is really about how much EGR do you want to use during that first 600 seconds? What timings are you using? So we did vary timing quite a bit. And if you're using any kind of intake throttling or anything like that, that's where that would come from. But we didn't have any extraordinary technologies that we were working with compared to some that are in the advanced research end. For example, if you're using a variable valve actuation system and you're able to open the exhaust valve early during cold start, you can dump a lot of energy to an after treatment system. We didn't have those options. So primarily the calibration was around those first level calibration knobs that you would turn. Downstream of the 600 seconds, it was mostly just EGR level changes that we were working with. Okay.
Ultimately, what was your fuel consumption hit, if any, over the FTP for the 0.02 NOx?
Yeah, we're looking at about a 2% penalty, but the aged parts have not been run. And if the aged parts require more aggressive tuning, we could have a bigger penalty. Yeah, I want to be very careful. This is definitely preliminary, and the after-treatment parts are not aged in the most traditional way. And so when we get the fully aged parts on there, that'll be the final piece.
I think we should leave it there, Charles. So
Okay.
thank you very much for sharing the
Thank you.
latest results. Very exciting.